actually, this is now in both places. The session is being recorded, everybody. And so, Linda, can you be kind of going after those slides that I just laid?
Already got them uploading.
Excellent. You're, I don't say this often enough, but you're very on top of things. You're a credit to your profession. Okay, so, wait, that's the wrong room. Linda, can you hear me?
Yes, I can.
Okay, now you can't see me because I'm lost here somewhere. Why don't you call up, I'm really trying to figure this out and I can't. I got too many browsers open here. Okay. Check to see if you have another window open. Okay, there, now I found you. And if I lose you, that's not good, but we'll see how it goes. Okay, please throw up the slides then, please.
I will just as soon as I finish uploading. It's at about 80% right now.
Okay, good. Probably I declare that I'm going to talk first, so I'll just start talking. This is the 13th week. Next week will be the 14th week. And we're in fine shape, but that had me thinking about what I want to do today. And today's class is going to be different than many of our classes have been, because we're going to talk some about ultrasound. And I thought about, no, I'm going to finish all the physics first, then we'll talk about ultrasound. But I said, you know, Jim, you really don't have to do that, because we've talked about a whole bunch of stuff already, and we can talk about those ultrasound things. So I'm going to mix it up, and we are recording this. So that'll be good for anybody who wants to study it. But tonight, Linda, we're going to have a lot of polls, okay?
Fun.
And things like that. And Linda, I'm also going to ask you to be a bit of a timekeeper. But I think in addition to the time, I really want everybody to participate, because, again, we're not grading you or anything like that. So I'm wanting everybody to participate. That means Linda might just keep things open until everybody's responded. And so there she goes. Okay, so this is my remarks. I told you what week we're in and everything else. This is what we're going to do. Jim is talking right now. I'll give Linda an opportunity if there's anything she wants to say. That's fine. And Linda and I talk frequently, but and probably more often than she might like. But anyway, if she has anything to say either to you or to me, you know, we can get that done then. The Q&A is anything you guys want to talk about, I suppose, within limits. And then we'll do that. This first poll, Linda, is kind of a wellness poll, or how, you know, how are you guys doing? And then we're also going to launch tonight LSA 14. You say, wait a minute, I haven't finished 13 yet. That's okay. I want to tell you what 14 is. And that's going to be due sometime in the 14th week. And then we'll start talking about ultrasound, which is something we've only done in a few problems, but we're going to talk some about it tonight. And I thought that might be a good way to do this. And Linda, that actually was based, even though you might not tie it in that way, that actually is based on a suggestion that you made me think of this. Okay, and Linda, we're going to be doing some polls in the midst of that, okay?
Okay.
So Linda, it is your turn. What do you want to say?
So nothing too major. If you guys are behind on assignments, then you can email me or Professor Bradley about whatever you're having trouble with, even if it's long past due. Feel free to just, you know, try to keep on top of it, okay? But we are here to support you no matter where you're at, so just let us know.
And they can also even, I mean, they can call us and text us and things like that, but they can also show up at office hours or whatever you call what you do. Okay, so that
absolutely.
That is good. Okay, now I'm throwing it out there. I know there's some of you out there. I really didn't count how many, but there's some of you out there So this is open for you. If you have any questions or comments and things like that, we'll entertain this for a little while. And I'm going to count to like about a beat of 6, and after that I'm going to be tired of waiting, but we'll see what happens. Okay, and yes, hello to you too. That is good. Okay, so I'm going to say that I think we're done with that, Linda. So why don't we do that little wellness poll, and then we'll move on to real work. And Linda does a really clever thing there. She juggles those things around so you don't always answer the same one. And I am so happy that the person that says great says, oh no, I thought that was the struggling block. No kidding, Linda. That's a good teaching practice, and you just do it natively, so that's good. And later on in the period, we're going to wait for everybody to respond. Now, Linda, we are in that count, yes?
Yeah, so there's 2 extras.
Okay. So there's 2 more people who haven't weighed in. And it's not that I don't care about you, but maybe you're, tending to one of your youngsters who, wow. I'm going to pose that question to, okay, well, first let me comment on that, and then we'll go up and talk about some of these comments that are on the screen. Okay, and there were a couple of people, or one person anyway, that was doing great, so that's good. There are a bunch of people that are doing okay, and one way I often answer that question when somebody asks me, Jim, how are you doing? I often say good enough, because things are not perfect in my life either. Like right now, I really wish I had a cup of coffee to suck on, but I didn't get that done before I came to the class. So anyway, that'll have to wait. So anyway, and if you're struggling, it's what Linda said. There's a lot of support out there. We can support you. We can make it way better for you if you can do that. And I'm sorry you're struggling, but there are fixes for that, at least with the course. Okay, Linda, the only one of these that I think is is a question, I'm going to throw it to you, because I know I'll answer it, but then I'll ask Linda. And Linda's answer will probably be more relevant because, some of you are thinking, yeah, but he's a guy or something. And Linda's certainly not a guy. But the other thing is, I am old and a math teacher, and Linda is young. And so she'll have a different perspective on this. 2 comments. I don't think there's an easy way to do much in life. A lot of things in life are difficult, and you step up to it, and you're stronger for having stepped up to it. So I don't think there's a magic wand there, an easy way to remember formulas. She's welcome to sing her song if she wants about the quadratic formula, but she doesn't have to do that. The other thing, though, I'm going to say is that actually the formulas just make sense to me. I think they're important, and that's why I remember them. And maybe they make sense to me because I've studied them a lot, but they do make sense to me. So it's not easy. Often I end up almost deriving the formulas anew. And I guess the last thing I'm going to say is, in this class, you don't have to worry about remembering formulas because there are grace notes, but you have to know how to use them. And someone chimed in here, and I'm going to say that first, and then I'll let Linda respond to this. Doing math problems helps me. And by the way, that's maybe one of the reasons that I do, because I've done a lot of math problems in my life. And so I remember formulas just because I've done them. Linda, you have comments on this, perhaps?
Yeah, so keep in mind what Professor Bradley said. You guys will have grace notes during the final, so don't feel like you need to memorize everything. It's more about making sure that the formulas make sense and that you understand what each variable means and what the units that you're working with are. So as long as you understand the context behind it, then you should be in decent shape.
Okay. And I had to parse her words because she was talking about being indecent, and I said, wait, but then it was in decent shape. Josh, what's up? Or Josh, your hand was up, or are you good?
Yeah, no. I lowered it, but so my question is, for the formulas in the grace notes,
Yeah.
will those formulas be labeled as to like not what the variables are, but what the formula, what the
Well,
purpose of
Josh, I'm going to tell you exactly what I'm going to do. Okay.
the. Okay.
I'm going to go to the, I'm trying to think of what to call it, end of the chapter summary. And I'm just going to cut those out and paste those into the thing. So, for example, we're studying chapter 7 right now. And at the end, actually, I'm finished with chapter 7 because I finished lecturing on it. But anyway, in chapter 7, at the end of chapter 7, right before the problems, there's this thing that's called chapter summary. And it's, oh, I don't know, it might be half a page or something. I just snipped that out for the most part. Now, Josh, I will do a little bit more than that because one of the things that will happen is we will be studying something in this course called the Doppler effect. And there are Doppler ultrasound applications. And it turns out that the equation in the physics book is a much harder equation than the one from the ultrasound book. And so I might cut that out and throw, no, in fact, let me tell you, I will cut that one out and throw that one in as well. But Josh, for the most part, Josh and everybody else, for the most part, I'm just going to go and snip those things out of the back of the physics book, at the back of the chapters. Josh, did I answer your question?
Yep, it does. Thank you.
Okay, excellent. Sydney has a comment. Yeah, Sydney.
So far we've done chapters 1 through 5 in the book.
No, we've done one. Well, that depends, Sydney. I'll tell you how many I've done because I have videos up there that cover things. I've done 1 through 5. I deliberately skipped 6 because we don't need 6. Now, it doesn't mean that 6 is a bad chapter or anything like that. We don't need it here. Okay? So that's
Okay.
why I skipped it. Then we did 7. And now, Sydney, we're ready for another quantum leap. And we're going to be leaping into some other chapter. But if you haven't watched the videos about 7 yet, make sure you're doing that. And, you know, that's kind of at hand here. Okay?
Okay. Thank you.
And in fact, this LSA 14 probably comes from somewhere else.
Was chapter 7 what you just posted today?
Well, Josh, and when I say Josh, I'm just talking to Josh because I want to call people by name when I can. This is really for everybody. I posted the end of chapter 7 today. A bunch of chapter 7 was earlier. Chapter
Got it.
7 was kind of kinetic energy, potential energy, elastic energy, energy, conservation of energy. And the thing that was in the last part that was posting was power today. So like we talked about in the lecture I posted today, it's kilowatt hours. We talk about that. That's a form of energy and things like that. So Josh, yes, today's posting was about chapter 7, but there was chapter 7 before that.
Tracking. Thank you.
Okay, excellent. Okay, Linda, let's look at LSA 14.
Okay.
Wow, LSA 14 has 2 problems in it. Okay, and I'm going to read them both. And you might say, wow, I don't know what some of these things mean. So you say, well, I guess I need to pay attention as we go forward because I'll learn what these things mean. And you'll understand what some of them mean anyway. Now, I was just going to ask you problem 65, which I'm going to read right now. But then, and I don't know how many of you were watching the news, but there was a very important thing that happened yesterday in the world of science, and that there was the launch of a commercial, not government built, a commercial spacecraft that took 4 astronauts up to the Space Center, and it was a successful launch. And that's actually kind of a big deal because Linda probably will go on vacations to the moon and things like that. I mean, that might very well happen. Okay, so I won't do that because I have other things to do right now. But Linda might make time to do that. But anyway, that happened. And when that happened, I thought, oh, we have to have a problem about astronauts. So I put 38 in there too. So you actually have 2. Okay. Is this the final LSA? Doubt it. No, I don't think it will be. And when is it due? I haven't thought about that yet. Linda, I'll ask you when you think it should be due in a bit. Okay. Okay. So anyway, but this is LSA 14. And I'm going to read 65 first. crude oil with a bulk modulus of 2.35 gigapascals. You might say, well, I know what a giga is, but what the hell is a pascal? We will be talking about that before this is due. Okay, that's a unit of pressure. That's named after the great mathematician Pascal, actually. He's a physicist and mathematician. So crude oil with a bulk modulus of 2.35 gigapascals is leaking from a deep sea well 2,250 meters below the surface of the ocean, where the water pressure is 2.27 times 10 to the 7th pascals. A lot of gigas and powers of 10 and stuff like that. Suppose 35,600 barrels of oil leaked from the wellhead. And this actually is, a social thing we can talk about too. Oil spills are not good, but it leaks from the wellhead. Assuming all that oil reaches the surface, how many barrels will it be on the surface? Now, there's going to be things you'll learn there. So you might say, I don't understand this today. Well, it's not due tomorrow, okay? And we'll talk about these things before it is due. Now I'm going to read the other problem. You have two problems this time instead of just one. Weighing astronauts. In order to study the long-term effects of weightlessness, astronauts in space must be weighed, or at least massed. You see they're floating around up there. In fact, I showed pictures of that. One way in which this is done is to seat them in a chair of known mass attached to a spring with a known force constant. And you see this is tying into some things and measure the period. Now, maybe you don't know what a period is, but you will before these are due, of the oscillations of this system. If the 35.4 kilogram chair alone oscillates with a period of 1.25 seconds, and the period with the astronaut sitting in the chair, probably strapped into the chair actually, is 2.23 seconds, find A, the force constant of the spring, and B, the mass of the astronaut. Okay. Now, Linda, this is, we're certainly going to be doing this, and this is week 13, Linda, I think. So when do you want to have that due? The end of next week or something?
Yeah, so I'm actually thinking December 1st, just because we do have Thanksgiving coming up, and their current assignment is due on Thursday. So that'll give them a little bit more time, especially since there's no tutoring on Wednesday or Thursday next week. So
well, Linda, how's
they may have more assignments, but this will give them more time on this one.
All right, so that will be excellent then. Thank you, Linda, for that insight. And Linda will probably, stick this somewhere where it stands alone, but it's certainly in here, and she'll tell you when it's due, and things like that. And I appreciate that's what Linda will do. And I also am going to mention that even though there's a Thanksgiving holiday and I want everybody to be safe, I'm going to tell you that I'm going to be doing math over Thanksgiving, and you can too. Okay, Linda, let's go to the next slide. Now, we're going to talk about ultrasound tonight, and there is going to be things for you to do later, but I'm just going to talk about what ultrasound is, and there's going to be some commentary and things like that. You might say, I know what it is, this is my profession. Well, maybe you do, maybe you don't. This picture is worth 1,000 words, though. And let's see, Linda, I can point here, can't I? So I'm going to point. So there's my pointer. I'll talk a little bit about, one thing is there's a smile on this person's face. And one of the things that's really important for an ultrasound technician is you damn well better be pleasant and put people at ease. I don't know if you have to tell them a joke, but somehow maybe you have a nice smile and you smile at them and they smile back. So that's an important part of this picture. This thing, and picture was taken long before COVID, but you wear the gloves anyway. And what you do is you have a thing here, and you can't really see it unless you're using your X-ray vision, but that's called a transducer. And we will talk about the physics of the transducers a little bit, but transducers are very fancy gadgets. They have a lot of software in them. They have a lot of piezoelectric rocks, and they're very sophisticated devices, okay? So that transducer is your wand. It's an important thing. And then you smear some goop on this person's stomach. And the reason you smear the goop is that there is air that is between the transducer and the stomach. And what you really want to do is have as nice a connection as possible between the two. So this goop makes the sound waves that go from the transducer into this person's abdomen, it looks like. And I'm guessing this person is pregnant, is what I'm guessing. And so anyway, this goop that you do is stuff that you do so that, and I'm going to use a fancy word here, but the impedance match better that way. So anyway, that's what this is. Linda, let's go ahead then to the next slide. There are many reasons to get an ultrasound. Perhaps you're pregnant and your obstetrician wants to have an ultrasound to check on the developing baby or to determine a due date. Maybe you're having a problem with blood circulation in a limb or in your heart, and your doctor has requested a Doppler ultrasound to look at the blood flow. Josh, this goes back to a discussion you and I had. We will talk about the equation for Doppler things, and I almost always ask a problem on that on the final. So, you know, Doppler ultrasound, and we will talk about that. Ultrasound has been a popular medical imaging technique for many years. It's a medical imaging technique that uses high frequency. And we're going to talk about frequency in this course. It has a definition, and it uses high frequency sound waves. And we'll talk about sound, and we'll talk about waves. What are these? And their echoes. This technique is similar to the echolocation used by bats. We looked at a picture of a bat earlier in this course. Whales do this, dolphins, and in fact, I understand the first use of ultrasound or sonar was used when they were searching for the wreck of the Titanic. And so, you know, there's submarine applications too. So we'll look at how ultrasound works, what type of techniques are available, and what each technique can be used for. Linda, next slide, please. Okay, so how does this work? Well, so you go to an ultrasound exam, and then you're the patient here. So you go into the room, and the technician, that would be you, and then there's an ultrasound machine. And if all the things happen, now that is not you, the technician, it is you, the patient, remove much of your clothes, okay? Now, not necessarily all of them, but enough to have the area of interest exposed. And the ultrasound, which is you, drapes a cloth over any exposed area that are not needed for the exam. And then he or she applies a mineral oil-based jelly to your skin, and that eliminates the air between the probe and your skin. And as I was saying, a fancy word for that is it does impedance matching. Okay, and then they cover the probe with a plastic cover because they don't want to have to clean that probe again. So the plastic cover keeps it clean. So he or she passes the probe over your skin to obtain the images. And the probe may actually even be inserted in you, depending on what they're trying to do. You may be asked to change positions to get better looks about the area. After the images have been acquired and measurements taken, the data, and that is data, just like we studied in the first part of the course, it's digital data, is stored on a disk. And you may get a hard copy of those images, or your doctor might show you one someday. Then they give you a towelette to clean up. You wipe the goop off, and you get dressed, and you leave. Now, as a technician, you don't really read these results. Now, if you're as good as I hope you become, you actually could do that, okay? And but it's not your job to tell a physician, hey, tell the patient, oh, you're just fine, or something like that. Somebody else does this. When I'm in class, I actually tell a story about that. Sometimes the technicians are actually better at this than the doctors, but I won't tell you that story today. Okay, so Linda, that's enough of this. That's what the exam is. Go ahead. Okay, this is what the equipment looks like. I said you had a transducer, and that's what we have here. It has piezoelectric crystals in it. We'll talk a little bit about that. It's got sound banking, and actually this is a very smart device. It's very expensive. It is not cheap, okay? And the transducer has controls on it too. So you can change the frequency, the duration, and the scan mode. You can turn it into a Doppler scanning mode, for example. And then the transducer really is connected to this CPU. It could be wireless, I suppose, but it's probably not always wireless. Often they have wires. And they'll go into the CPU, which stands for Central Processing Unit. And it's got a keyboard. It stores stuff. It can print things. And there's even a display. And the ultrasound technician may look at the display from time to time just to make sure he or she is getting a good image. Okay, Linda, next chart. And by the way, it looks much like this today. I mean, it hasn't really changed that much. The displays are a little better and the CPUs are smaller and stuff, but otherwise it's about the same. Okay, the following events happen. The ultrasound machine, that's really the transducer doing this, transmits high frequency. Now this is 1 to 5 megahertz. And we haven't defined what a hertz is right now, but it's a unit, and mega means a million. So it's 1 to 5 megahertz. So this is a very high frequency sound, pulses. And that's another thing you should know, is it's not a continuous sound, it is a pulsing sound. So it's on, off, on, off, on, up. That'll come up in tonight's lecture, in fact. So it sends these pulses into your body using the probe. The probe is called a transducer. The sound waves travel into your body. Linda, do you want to read these, or am I doing fine?
No, you're fine.
Okay. And I don't want Linda to feel unappreciated, because she is appreciated. The sound waves travel into your body and hit a boundary between tissues. Now this might be between fluid and soft tissue, and it might be near a bone. And what really happens is there's reflection that happens. So some of the sound waves get reflected back to the probe, while some others travel further. We'll talk about that as well, the phenomenon that's happening there physically, until they reach another boundary and then perhaps get reflected. Now, and by the way, the reflected waves go back to the transducer. And the transducer, it speaks, but it also listens, and it relays that to the machine. The machine calculates the distance from the transducer to the tissue or organ where the bounce happened, using the speed of sound in soft tissue. Now, this article uses this number, and we're going to do a problem later that uses very much this number. We'll let you know what to use in a thing, but the speed of sound in soft tissue is what we're talking about, and the time that each of the echoes return, usually on the order of millionths of a second. So you see, this is very sophisticated equipment. So you see the frequencies are very high, but the times are very short. The machine displays the distances and intensities, and actually it uses software processing to make that into pictures. And I guess it said that here, 2-dimensional pictures. And millions of pulses and echoes are sent and received each second. The probe can be moved along the surface of the body and angled to get various views. By the way, guess what? When it's angled, we use trigonometry to figure things out. Linda, let's go to the next slide, please. Okay, there's all kinds of different ultrasound. The ultrasound that we've talked about so far is a 2-dimensional image or a slice. You can do 3-dimensional ultrasound things, and there's 3-dimensional, and that's Doppler and, wow, that's not spelled right, it's D-O-P-P-L-E-R, it's someone's name, Doppler ultrasound. And we'll talk about a bunch of this stuff. And 3-dimensional imaging is important. In fact, when my grandson was being born, my son spent, which really surprised me because he's a very conservative guy, but he spent a whole bunch of money getting 3D ultrasound pictures of my grandson, Grant. Okay, and certainly it can be better, and here's some more applications. And Doppler ultrasound is based on the Doppler effect. That is weird, what happened there. When the object is reflecting, the ultrasound wave is moving, it changes the frequency of the echoes. We'll talk about how that happens, creating a higher frequency if it is moving toward the probe and lower frequency if it's moving away, and you can do that calculation. And you see people are interested in that because they want to know, well, is your blood flowing the way it ought to or not? Okay, Linda, let's go to the next slide, please. That's pictures of ultrasound things, and I'm sure you've seen those. Linda, let's go to the next slide. Okay, it's been used in a variety of, so obstetrics, gynecology, cardiology, and cancer detection. The main advantages of it is that you can observe without using radiation. Now, some people think that there's heat energy that happens, and certainly safety is a consideration, but it's considered safer than most. Ultrasound can then be done much faster than X-rays and other radiographic techniques, and here's a list of the uses.
Not sure that's going to show up. There it is.
Okay, now we're going to have Linda read this. No, we're not. I was kidding, Linda. You don't have to read this, but gee, that's a boatload of applications. It makes this a good thing to do. Linda, go to the next slide, please. A growing use for this as a diagnostic tool in emergency rooms, and in fact, on fields of war. So they're making these things smaller and more portable. There have been concerns about the safety of ultrasound. It is energy. Hey, we've studied energy, haven't we? So ultrasound is sound energy, and says, what is this energy doing to the tissues of my baby? And talks about there have been some reports of low birth weight babies being born to mothers who had frequent ultrasounds, but actually low birth weight babies are often handled just fine. It depends. And so it can develop heat, and it also can cause bubbles to happen when dissolved gases come out of a solution due to the local heat caused by the ultrasound. If you think about that, both those have to do with heat. However, it's considered pretty safe, but only to be used when necessary. You guys, I think, will have good opportunities for jobs because I think there's going to be more and more of this. Linda, next slide, please. Okay, in the future, I think I probably said a bunch of this. Virtual reality might happen where people just are wearing, like goggles when they're doing it, and these things will get smaller and more portable. Linda, next slide, please. Okay, now we're going to talk about something, and I think Linda said that I can write here. So I'm going to try to, no, actually that's text, but that's fine. This is something that's in your syllabus. It's something you have to know. And I don't know, I certainly haven't written your final exam yet, but I expect there will be a problem about this on your final exam. And it is called the range equation. Like home on the range. Okay. And so, and I just tore these out of an ultrasound book. Now, and by the way, you might want to take some notes about this. I actually borrowed an earlier version. This is from my version of the book. I bought the book. It cost me $138, but I bought it anyway because I wanted to do a good job teaching you guys. I had an earlier version of this book that Melissa, who is your program coordinator, had in her office, and I kind of took it with me. And actually, it was the one that Melissa studied from. And Melissa, and I'm not making fun of her, I'm just saying she's a serious student, but I did look at her book, and she underlined every word in the book. And I don't underline every word in the book just because, well, you might as well memorize the book. But anyway, so here we go. So this is the range equation. It's something you need to know how to do. So to create an anatomic image, a sound pulse must travel to a reflector located in the body. Okay, so it goes down, it hits something, then it bounces off, and then it goes back to the transducer. So it returns to the transducer. Now, the travel time of this journey allows us to accurately position the reflector. We say, oh, we know where it is because of those calculations we had. So that gives rise to what we call a so I have 2 pointers.
Yeah, I'm pointing too.
Oh, good. No, that's good. Oh, wait, Linda points. That's good. Linda's point. Yeah, Linda, that's good. Please, that actually helps, and I won't be confused. All right, so time of flight or go return time. Now, those phrases are used. So ultrasound systems determine reflector depth by measuring a pulse's time of flight with a very accurate stopwatch. It's not a stopwatch. It's a very elaborate timepiece, though. The elapsed time from the pulse creation to the pulse reception is called the go return time, or time of flight. Now that means it flies down to, for example, a bone, and it bounces back. So it goes and it returns. And so that's what happens there. When a reflector is located superficially, now that means not deep, okay? So when it's close to the surface, the time from pulse creation to reception is brief because it moves pretty fast. Whereas trips to and from deeper reflectors require more help. I think it's really cool that we both can point at this. That's great, Linda. I certainly not going to be pointing at it all. That's good. Okay, let's see. All right, so that's called the go return time. And I guess I said most of that down here. The time of flight is directly related to how deep the pulse travels. Greater distances prolong the time of flight, and lesser distance shorten the time of flight. And Linda, we're going to be looking at this figure over here, this whatever 7:1 or whatever. So at the top you see like thing that looks like well, I don't need, it looks like a donut or something, but it's something that's down there. And so you got, and that's supposed to be a picture of a transducer. So it sends the pulse down there, it bounces back, and it comes back. And here, then the next one, you see one where the green donut is moldy, and maybe it's been there for a while. But anyway, it is further away. So as it says underneath, time of flight of an ultrasound pulse is shorter for shallow reflectors, and I guess the color does show up. That's purple, and longer for green. Okay, so that's good. Okay, so Linda, let's keep going then, please. Okay. Now, ultrasound computers are programmed with an average speed of sound in soft tissue of 1.54 millimeters per microsecond. Now, I'm looking at the time, and we're doing just fine. But if this were a longer thing or face-to-face class, I'd say, hey, guys, why don't you change that 1.5 millimeters per microsecond, change that to miles per hour or something? And that could be a question I suppose I could ask somewhere along the line, and you ought to be able to know how to do that, such a thing. Now, since this is the average speed of sound in soft tissue is known, the time of flight and distance that the pulse travels are directly related. And we talked about what a direct relation was too. We said that y is directly related to x if y is equal to a constant times x. But here we're talking about distance, and we're talking about velocity and time. So distance equals velocity times time. And that's the equation that we're talking about here. They're boiling it down a little differently, but that's what we're going to talk about. Now, Linda, we are going to do a poll here, and let me describe the poll. Now, you see, you're having this sound wave go in soft tissue. And let's just think about a classroom at COD. Do you think sound travels faster in the soft tissue or through the air at COD? And Linda, you understand the two questions, or the question I'm asking?
Yes.
Good.
So
Okay.
which one is faster?
Right. And I want you guys to vote because Linda is going to be counting how many people there are and stuff. Not to take attendance, just because we're going to let people respond. So make sure you do respond to this, and we'll see how Linda ends up writing that. I'm sure it will be excellent. Yes. Which is faster, the speed of sound in soft tissue or air? And vote. Please play. No one knows what you're answering. And this is very different than the classroom, because in the classroom you might say, hey, Susie's really smart. How did Susie vote? But you can't do that here. Please, I really want everybody to play. I mean, we won't wait forever for this, but well, 8 of you learned something because it travels, or excuse me, 8 of you learned something, and it's going to travel faster in soft tissue. Okay, and we'll talk about the speed later, but okay, so that was just an aside. Thank you, Linda. Okay, in fact, the depth of a reflector can be accurately calculated from the go-return time using the following equation. So here's an equation. And Josh, this is going back to what you and I maybe talked about with your question before. I got to get my hand off there. Linda's hand is fine. I might, and Zach, or not Zach, but Josh, Linda knows why I said Zach. Josh, it depends on if I'm at the top of my game, but I'm usually pretty good, pretty close to that. And so I probably will go and cut this out, because this is not an equation you find in a physics book. The physics book will tell you distance is velocity times time. But you see, that's exactly what's happening here, because you see the go-return time is measured in microseconds, and this is millimeters per microsecond. So what you do is if you multiply those guys together, the microseconds whack with one another. And the reason it's 2 is because you're going and you're coming back. So the depth of this thing in millimeters is given by that equation. Okay, so, and that's perhaps that is what they call the range equation, I suppose. Okay, note, when one reflector is twice as deep as the other reflector, the pulse's time of flight is twice as long for the deeper reflector. Of course, that's what directly proportional means. Let me go to the next slide, please. They also call it, and this is like, I don't know, ultrasound vocabulary, but they also call this the 13 microsecond rule. And you might be saying, which is actually what I would say is, why don't you just have one thing and call it one thing? But they don't. So anyway, here we go. The 13 microsecond rule, and I think if you look in our course objectives, I'm supposed to talk about the 13 microsecond rule. So the 13 microsecond rule always applies when sound travels through soft tissue. For every 13 microseconds of go-return time, the object creating the reflection is 1 centimeter deeper in the body. Not millimeter, it's centimeters, and units matter. So for example, if you have a pulse's time of flight is 26 microseconds, then the reflector is 2 centimeters deep. If a pulse's time of flight is 39 microseconds, then the reflector is 3 centimeters deep. Since a pulse, I'm sorry, Linda, I keep messing with I need to get off there. Oh, I know how I'll do it. I'll get rid of that. That's good. I got rid of it. Okay, since a pulse travels to the reflector and back, the total distance that a pulse travels is twice the reflector. And you see, you really want to pay attention to the wording of the question, because sometimes students don't read the question. Sometimes I'll ask, how deep is something? Sometimes I'll ask, how long does it take to get there, and so on and so forth. And there's a table up there, and you can see what happens. And we did the first 3, but you can see that the total distance traveled is double the depth. And you can get those other numbers too there. Okay, Linda, next slide, please. Now, and I really thought a little bit about this before I, threw this into the presentation, but we are going to talk about period later. But now we're just saying pulse repetition period, and that's the time between it firing pulses. So let's think about that. Your transducer speaks, then it pauses and it listens, and then it speaks again. Okay, so the period is the time from when it first speaks to when it speaks again. That is a period. And Linda may show you in that figure the period up there on the top thing. You see, it's like the red thing. So you're going from the same place to the same place. I don't know if I like the way they drew that, but that's a different period than the one underneath it, because the one underneath it and period is like time. Okay, so it's the time between pulses is what a period is. Okay, so that is good. So when a ultrasound person adjusts a system's maximum imaging depth, and that is something you do because you say, well, we're trying to figure out what's going on here, so I have to set my imaging depth on something. The pulse repetition period is altered, and we looked at that picture already. Recall that the pulse repetition period, and by the way, there's a lot of acronyms here too. They call it PRP. And you say, well, I don't remember what PRP is. Well, you should, because they're going to say PRP. Yeah, is the time. Thank you, Linda. That's wonderful. No kidding. It is great working with you. From the start of one pulse to the next pulse, I already said that. And the pulse repetition period is the go-return time of a pulse between transducer and that. And so the 13 microsecond applies because you're going through soft tissue. Now, it is important for you to realize, though, these next points. So when the depth of a view is shallow, the PRP is short. When the depth of view is deep, the PRP is long, because they are directly proportional. Let's go to the next slide, Linda, please. Thank you. Okay. Mathematically, then, the pulse repetition period in microseconds, because it is time, is the imaging depth in centimeters times the 13 microseconds per centimeter, and the centimeters whack one with another, and then you have that. And so here's some examples. In the book, that's not blue, that's purple, Linda, I think. But there it says what I said. It's directly related because it's directly proportional. So it's directly related to the maximum imaging depth. And for example, over here, when the depth of view is set to 10 centimeters, it's going to be 130 microseconds. When the depth of view is set to 5 centimeters, it's going to be 65 microseconds. Okay, Linda, please advance the slide. Now we're going to talk about another thing. And Linda, yeah, I did a kind of a shabby job of doing that, so you can probably figure out what that is just by the context. All right, now we're going to talk about something else, though, and this is called pulse repetition frequency. Okay, and so you might say, how often do I talk to my brother on the phone? And I would say something like, I talk to my brother, I might say 3 times a week, but I might also say 1 time every third of a week or something. Anyway, I could talk about the frequency. I don't think I did a good job with that example, but anyway, frequency is how often something happens. Okay. My parents, I have a sister and a brother. I'm the oldest, but there was almost exactly 2 years between each of us. So we could say the frequency of my parents having children was once every 2 years. Now, you see, this is 1 over time, and we'll learn more about frequency later. It's a really important thing. But anyway, pulse repetition frequency is you do 1 cycle, that's 1 on and off thing, like speaking, back to speaking again, per what unit of time. So you see, it's related to the period, but it is different. So this is called the PFR, pulse repetition frequency, and this is the maximum imaging depth. So the speed of sound in soft tissue is that, and they change it to centimeters per second. So in 1 second, sound can travel into the tissue and return from a depth of, now this is a calculation you have to do because in 1 second you go down and back, but the depth can be 77,000 centimeters. At first, this statement may appear silly since 77,000 is a big number and 77,000 centimeters is nearly a half mile. However, this also means that sound can travel back and forth 77 meters, a total of 1,000 times in 1 second, or to and from a depth of 7.7 centimeters 1,000 times in 1 second. Okay, and so you see this might be a whole bunch of trips, but that is what's happening. Okay, so and here's the equation for this. Mathematically in soft tissue then, sorry Linda, I'm pointing again, the pulse repetition frequency. Now, frequency happens in, yeah, Linda said I must have miscalculated that in my head. That happens a lot too. Okay, but over here on the other side, so then the mathematically in soft tissue, the pulse repetition frequency, and the units on that are hertz. And we really haven't talked about hertz yet. This is named after Heinrich Hertz, a great scientist. But Heinrich Hertz, this is 1 cycle per second. Okay, so you see, this is hertz, but it might end up being many cycles per second. In fact, when I say 5 megahertz, that means 5 million cycles per second. But anyway, the pulse repetition frequency in hertz is, and you look at these units, so it is 77,000 centimeters per second divided by the imaging depth, which is in centimeters. Now, if you think about what's happening with those units, the centimeters cancel one with another, and a hertz is really a reciprocal second. It is 1 over second. And I got to tell you, when I was a youngster, that actually bothered me a lot. It doesn't bother me at all anymore. But anyway, you want to think about what hertz are. Okay, and let's see. So when the depth is shallow, the PRF is high. And when the depth is deep, the PRF is low. And if you look at that equation, you'll say, oh yeah, it's inversely proportional. That's what's in that little purple box there. And that's probably enough, isn't it, Linda? Yeah, let's go ahead. And you guys can go back and look at this because Linda records the video. So we're advancing the slide. And now we have some questions to answer. Now, Linda, this is where I'm going to ask you, and I don't know, Linda, I don't know if I don't really want to do these. Well, first of all, I want everybody to think about these and answer these. Now, these are multiple choice questions, and I don't ask multiple choice questions very often. But I got to tell you, on your certification exams, it is littered with multiple choice questions. They like it, and I understand why they do, and I understand why I don't. But anyway, here's a problem. And Linda, I don't know if we can do 2 of these at once, or if we can do 2. You know what I mean? I'm trying to.
Yeah, we can only do one at a time.
One at a time. That's fine. So we're doing number 1, and Linda might. I don't know. She may record the statistics or something like that. But Linda, we're trying to get So this is number 1, and we're trying to get everybody to vote. Now that means we're looking for 17 voters, or Linda will get impatient and we'll move on. I don't know, some of these might be, putting Band-Aids on their child's knee or something. I mean, who knows what's going on there. I think we're just going to, all right, so Linda, maybe it's worth capturing that that D was the most popular.
You got it.
Although actually, when I said it's more popular, and D would have won a presidential election if that happened, but they only got, well, now they got 7 out of 12. They really would win an election there. Okay, so that's D. Linda, let's go to the next one, number 2, and post a poll. I should read number 2, maybe. Linda, I'm going to turn off your poll on my screen, but that doesn't turn it off on anybody else's side. Sound wave is created by a transducer. It reflects off an object and returns to the transducer. The go return time is 26 microseconds. What's the depth of the reflector? Okay. And somebody's asking a question there, but Linda, that looks yellow to me, and I can't read yellow.
I got it.
You know what it says?
Yeah, will the final exam questions be like this? And the answer is no.
Well, the answer is no, but there won't be any A, B, C, and D. But I could ask you a question like that, but then you'd have to do the calculation, and you'd have to write 130 microseconds. That was the most popular answer. Okay. And are people polling on this next one? Jessica has a question, I guess. Yeah, Jessica.
Okay, how are we figuring out the answer?
This is using the 13 microsecond rule.
Okay, so do I times it, divide it? I'm lost.
I'll tell you what, when we go back, what we might do is we'll check the answers, and if you still have a question, maybe I'll ask Linda to do that if she wants to do that. Okay, so Linda said people voted for number B. Let's look at the answers. And Jessica, well, let's look at answers. Go to the next slide, Linda, please.
Okay.
Okay. Now, Jessica, I think this answers your question completely. Now, it's not always going to, and it looks like students got both the questions right, or at least the majority did. Now, if you got it wrong, you have something, to learn or remember, but that's okay too. So Jessica, it looks like you take 10 centimeters times 13 microseconds per centimeter and get that. You good, Jessica?
Yes, I got it now. I was confused.
Okay, but we fixed that, so that's good. Number 2, the answer was B, and Linda said, and Linda, I didn't even see the poll. Maybe everybody said that, and maybe we don't have to talk about that. Let's go to the next question. All right, this is number 3, and Linda said it's good to do these one at a time. Let's do this one at a time. So everybody do number 3, and Linda will circle an answer whenever she thinks enough people have weighed in. And then we'll move to question 4. I will read this, I'm sorry. A sound wave is created by a transducer, reflects off an object, and returns to the transducer. The go return time is 26 microseconds. What's the total distance that the pulse traveled? And Linda will just circle something whenever she thinks it's the time to do that, and then I'll read number 4. Okay, let's look at number 4 then. I'm going to read it for you. The maximum imaging depth of view during an ultrasound exam is 10 centimeters. Now the sonographer adjusts the imaging depth to 20 centimeters. What happens to the pulse repetition period? Oh, Jessica's hand's up again. I'm sorry, Jessica.
Is it going to show us how the questions, you got the
I'm going to
answers?
show you an answer, and if it's not, and I got to tell you, I don't know what it'll show, but we'll see it. And if it's not good enough, then we'll talk more. Okay. All right. So okay, Linda marked those. So let's go to
I did not mark that, but somebody's marking it.
Oh, somebody crossed out. Oh, well, yeah, and by the way, that's the issue. This hinges on, do you know what pulse repetition period means? And so, yeah, it's B or C. Let's move on then and look at answers. Okay, it's D, twice the distance. The distance traveled is twice the depth of the reflector. And number 4 is C. And I'm just reading what it says. Pulse repetition period is directly related to the imaging depth. So when the imaging depth doubles, pulse repetition period doubles. Now, Jessica, I'm not picking on you, but are you okay with these answers?
So question 3 is D, 4 centimeters.
Yes.
But how did you get that with only 26?
Linda, do you mind drawing on the slide or something to talk about that one?
So they're talking about the go return time is 26 microseconds. So we know that the depth for every 1 centimeter is 13 microseconds.
The time, right.
Yeah, so if they're telling us that it's 26 microseconds, then 2 times 13 gets you to be 26. But that is the depth, not the total distance traveled.
Okay, maybe that's what I was missing was the 13.
Yeah, so we know that the receptor or whatever is 2 centimeters deep, but they're asking for the total distance here, not how deep it is.
No, I get it now. I just was missing the 13. I was trying to figure out. I get it.
Okay.
Now, because I was trying to figure out the missing number. Like, wait, what's 20? I get it now.
All righty then, Linda. Next slide, please. I am watching the time for you guys. I'm not getting lost. No more lost than I usually am. Okay, we got 3 questions here. The maximum imaging depth during an ultrasound exam is 10 centimeters. The sonographer again adjusts this to 20 centimeters. What happens to the pulse repetition frequency? In fact, I'm going to let you go. No, we're doing these one at a time. That's what Linda recommended. I think that's the only way to do this with polls. Okay, so answer, please. Linda will mark an answer up there when she thinks we've got a critical mass on an answer. And then we'll move on to the next thing. Okay, so I will turn that off and I'll read the next one then. Here we go. Okay, the imaging depth during an exam is 10 centimeters. The ultrasounder adjusts the imaging depth to 5 centimeters. What happens to the pulse repetition period? So pick one of those answers, please, and Linda will watch a poll And when enough people have weighed in, she'll circle what seems to be the voting answers. But by the way, you could vote and be wrong. I mean, that can happen, but we'll look at the answers in a bit. Okay, I'm reading number 7 now. A sound wave is created by a transducer, reflects off an object and returns to the transducer. The imaging depth is 10 centimeters in soft tissue. You see, what we're really doing, folks, is we're doing distance equals velocity times time. What is the maximum pulse repetition frequency? Okay, we're going to look at all these answers. We're going to look at that one first. So let's go to the next slide, Linda, please.
Okay, we got a tie on this one, so I'm waiting for them to decide.
Oh, can they break the tie? Okay, that's good. Abby maybe has a question. I don't know.
I'm sorry, I hit that on accident.
Oh, that's okay. That's okay.
All right, looks like B is the winner for that. So we
Okay.
got 3 Bs.
Okay. Where was everybody else? That doesn't matter. Let's go to the next slide. B is the correct answer, but the only reason you knew that was it's the only one that has the correct units. See, frequencies come in hertz, so kilohertz is frequency. Response A has no units at all. It can't be right. Response C, that PA stands for pascals, and that's a unit of pressure. We'll talk about that soon, but it's not kilohertz, so it's not hertz, it's not kilohertz, it's not megahertz. That couldn't be the answer. And the last one is time, microseconds. But we were asking for frequency. Frequency only comes in hertz. And then the answers were B, and I think we probably got those right, didn't we, Linda?
Yeah.
Okay. Someone just said that they're liking this lesson. I enjoy the last part of the course too because we've studied all the physics. Now, by the way, we're not finished studying physics, but I decided this would be, I have to do this anyway, and we've studied enough to do this now. Okay, so let's go, Linda, to the next slide, please. And I am watching the time for you guys. There's 2 questions here. At number 8 is a sound wave is caused by a transducer, reflects off an object, returns to the transducer. The maximum imaging depth is 7.7 centimeters. What is the PRF? And I'm going to read it, just leave it as PRF. You're supposed to know what that means. A has leapt into the lead as the response, at least the way I'm seeing it.
Yes, it has.
A lot of people aren't playing, but anyway, okay. So anyway, Linda, should we shut this off or wait?
Let's give it another minute or two.
Okay,
See if
Linda,
we can get a stronger lead.
Okay, you're making the call.
There we go. All right, now we'll call it at 8.
Okay, good. Okay,
oh,
so
dang.
then,
We're back at tied.
whoa, okay. Well, let's do this. Some of you are going to learn something on this. In fact, I hope a lot of you learned something. Number 9, a sound wave is created by a transducer, reflects off an object, and returns to the transducer. The go return time is 130 microseconds. What is the maximum PRF? So find an answer, please. Linda, we can make this public. I've decided I'm not afraid of that.
Okay.
Again, don't worry, I am watching time for you guys, so we're fine. What's happening there with the poll? And
A has a little bit of a lead.
let's see. Do I need to? I can view the poll myself. I was not punching the right button or something. Okay, now I know how to do this.
There we go.
Okay, so Linda, let's advance the slide and look at answers for this problems. Okay, the answer to that should have been A. Was that our winner? And
For number 8, it was tied between A and C.
Okay.
For number 9, we did have a winner with A.
Oh, 9 wasn't A. Oh, yes, I was looking at the wrong one. Okay, hopefully people see that, and that just comes straight from the equation. Now, Linda, if we go back, we end up screwing up the video, right?
We can go back.
Well, I know we can, but doesn't it erase and re-record on the video? I'm asking a very technical question for me.
No, it just erases the writing on the screen.
Okay, I know that when I'm doing MP4 encoding, if I go back, it erases what I recorded on the previous slide. But I don't know what's happening here. Let's go back to Linda. Would you like to answer the question? It was so how did you get an answer for this number 9? Are you comfortable with this?
I'll let you do it.
Okay, then I'm going to ask you to go back
Okay.
to the equation for PRF. And that might be erasing all kinds of stuff here. PRF, yeah, it's here. No, keep going. Because no, we should be going the other way now, forward.
Yeah.
There it is, another time. PRF, there we go. Okay, so you see the equation is going to be 77,000 centimeters per second over that. So you see what we're solving for, I think, Linda, and I don't have that in front of me now, the thing, but I think we're solving for what is the maximum imaging depth. And in fact, I would just solve this for imaging depth, and we would have that solution. I'm really curious. I might look at this video and find out what that did when we went back. Maybe that just records as we go along, which actually that's the way I wish it was. Okay, so that's our equation, and so its PRF is 77,000 divided by imaging depth. Go back to the slide where we were on, Linda, where that question was asked.
Okay.
Please. I wanted to show the student where the equation came from. Okay, so here then I'm writing, and so this is going to be PRF is equal to
so that was 77,000 centimeters per second.
Right.
Divided by the imaging depth in centimeters.
Okay, so, and we were to find the maximum PRF, okay, and it was the imaging depth, and so the go return time was 130, and since the go return time was 130, that means it was 10 down, right?
Yeah.
Now, and Linda was talking about units, which is a good thing to do. So this is centimeters per second divided by, and this was centimeters. Okay, so that means that what happens is that the centimeters will cancel, and one of those will cancel, one of the zeros will cancel, and it's 7/7, and that's the reciprocal seconds. That's 1 over seconds, and that is what a hertz is. So I hope that answered whoever asked that question. If not, ask some more, but that's how I work the question. Okay, Linda, let's see. You know what, Linda? Time is up. Let's go to the next slide just so I can see what it is. We're not really covered.
Real quick, the 10 came from the go return time being 130 microseconds. So we used the 13 microsecond rule to determine that the imaging depth was 10 centimeters.
Thank you, Linda. I didn't even see that question, so you're more observant than I. Okay, let me see what the next slide is. And the only reason I'm doing that is, yeah, we might talk about some more of the stuff. You guys can certainly read it, but we're finished for tonight. I have office hours, and Linda, this is recorded, right?
Yes.
And your life is such that you can do that, or should I help with that?
Yeah, I can post it tonight.
Excellent. Thank you so much, Linda. And again, it doesn't have to be untitled. She was so more not focused on that you know, I was worrying for nothing. Okay, I'll have office hours at 7:30. Good night, everyone. Be careful. And
Have a
Linda,
good evening.